Alright. So let's find the parametricization of the graph I'm about to put up here. Alright, so here's the graph. This is in your ebook. You might want to do a little rough sketch of this though, because it's not too hard to graph. You can see it has 3 parts. So each part, we were talking about a curve being partitioned. This smooth curve C has been partitioned into these 3 different curves. Alright, so what we need to do is we need to figure out how to get from, we need to figure out the equations, how to get from one point to the next point, like from the first point to the next point. And so we need to figure out an equation for x of t, y of t, and z of t. And we're going to start off, for this first curve, we're going to let t be between 0 and 1. Okay, so if we look at the 2 points, we look at this point right here that starts C sub 1, and we look at this point right here that would end here at C sub 2. You see the direction this is going. Alright, and so to get from 0 to 0 on the x, that would just simply be 0. Now to get from 0 to 2, I would think about that. I mean, there's a couple of ways you could get from 0 to 2. And this function is of t. But the thing is, okay, so whatever equation I come up with, whenever I plug in 0 for t, I want to get out a 0 for y. And when I plug in 1 for t, I want to get out a 2 for y. So what kind of equation could I come up with that when I plug in a 0, I get out a 0. When I plug in a 2, I get out a, when I plug in a 1, sorry, I get out a 2. Would that work for 2t? If I plug in a 0, I get out a what? 0. If I plug in a 1, I get out a 2. Alright, so that's my equation for y of t. So now I want to figure out an equation for z of t, 0, 0. So don't matter what I plug in there, there's no variable, right? I'll always get 0. So that's my 3 equations. That's the parametricization of C sub 1, where if I let t start off at 0 and then go to 1. And that would work for any point really in between C sub 1 and any point between my initial point and starting point. That would give us these values here. Okay, but usually we let t be whole numbers when we talk about it. So it'd be like t equals 0, t equals 1, t equals 2, t equals 3, that kind of thing. Okay. So we want to do the same thing for c sub 2. All right, we want to figure out the parametric equations that would get us from where we start c sub 2 and where we end c sub 2. That's this segment here. So for that segment, we're going to let t be greater than or equal to 1, less than or equal to 2. All right, so we're going to figure out an equation for x of t, y of t, and z of t. All right, so look at the x coordinates here. We want to go from 0 to 1. But not only do we want to go from 0 to 1, when we get out of 0, we want to plug in a 1 for t to get out of 0. Okay? We want to plug in a 2 for t to get out of 1. I know I'm stretching your brains a little bit here, but we have to figure out equations that when I plug in a 1, I get out of 0. When I plug in a 2, I get out of 1. T minus 1. All right, let's make sure it works. Plug in a 1, 1 minus 1. Yes, that is 0. Plug in a 2, 2 minus 1. Yes, that is 1. So that will work. All right, so now look at the y term. I want to go from 2 to 2, so I don't want to change. So when I plug in a 1, if there is something to plug in a 1 for, I want to get out of 2. When I plug in a 2, I want to get out of 2. So it would just be 2, right? If I find y of 1 here, it's equal to 2. If I find y of 2 here, it's equal to 2. There's nothing to plug in for. All right. Lastly, 0 to 0. Okay, so that's going to be 0. All right, we have one more segment. I'll write it right here, c sub 3. For c sub 3, we're going to let t be greater than or equal to 2, less than or equal to 3. So 2 and 3 are the values we're going to use for t here. And we have a x of t, a y of t, and a z of t. I'm making them up. So if I make up different values for t, I want the same increments, like the same sizes. But let's say I decided to half all of that. Then t would be between 0 and a half. It'd be between a half and 1. And it'd be between 1 and 3 halves. But that's going to change my equations. That's okay. So that these answers aren't unique. But for these values of t, this is what I'm getting. Okay, that's important. That was a good question. All right, so now let's look. We're going from, so we see our c sub 3 here. We're going from here up to this point here. So we want to go from 1 to 1. So, yeah, that's right. If I plug in a 2 or if I plug in a 3 here, I'll still get out of 1. From 2 to 2. 2. Now see if you can get this one. 0 to 1. But when I plug in a 2, I want to get out of 0. When I plug in a 3, I want to get out of 1. That's right. Plug in a 2, get out a 0. Plug in a 3, get out a 1. Alright, so once I write down and I do the parametricization of each one of those parts of the partition, of the 3 partitions of the smooth curve C, then I can write a piecewise smooth equation. And so remember, we use R of t to represent our vector valued function. All right. Now, the way that we do this, of course, you know, with a piecewise function, we're going to break it into pieces. And we're going to have our conditions over here for t. Okay. And now this is where we're going to use I, j, and k for each one of our pieces, each one of our functions. So if we look back up here for C sub 1, C sub 1, we had a 0, a 2t, and a 0. The 2t is with y of t. So this is going to be 2tj. Alright. Now for the next function, for the next parametricization here, I had x of t was t minus 1, and y of t was 2, and z was 0. So we won't have a 0, we won't have a k component. We'll have t minus 1 times I plus 2 times j. Alright, and on the last part, C sub 3, we did have an answer for all of those. So that's going to be 1i plus 2j plus, and then make sure you put this in parentheses, t minus 2k. Kind of neat that we could do that. I mean, then we could find all kinds of things if we needed to. But that's how you do the parametricization of a smooth curve C that's partitioned into different pieces. You got to take one piece at a time. That's the answer. That is the, what is it called? The piecewise smooth parametricization. It's a little different. It's just a way to write, you know, an equation of, if we had something, maybe we have something traveling in that path. Who knows? Maybe it's an electron, or maybe it, you know, it's some type of energy that's moving in that certain direction. And those answers again aren't unique, because if I change t, then I change the equations. The funny part about it is, to me it's kind of funny, is that it will still have the same properties though. If I start doing other calculus to it, it'll still have the same properties. One of those properties is work. It will still do the same amount of work to get from the first point to the last point if you change the values of t. So, but we're going to get into that. That's something we're working towards. No pun intended. Working towards. Looking at the work. Man, I'm so funny. Is that why y'all are laughing so much? You're laughing with me, right? All right. So, once we can do that type of stuff, you know, we're going to use that to do some other stuff, but this is where we start talking about line integrals. All right. All right, so if we wanted to do a line integral along some smooth curve C, so that would be like integrating over that entire curve we were looking at, C. The notation that's used for that is this, so it'd be like the integral over the curve C. It's the integral of f of xy, or xyz, so on and so forth, ds. Now the ds here is what's a part that you may or may not know that we've went over before. It's similar to some of our arc length stuff that we've done in a way. But I'm gonna tell you some of the official definitions, and then we'll get into it, and I'll show you actually how to find it, how to figure it out, how to do it. All right, so this ds here is moving along the curve C. All right, and this C, this is the same C that we're talking about up here. So instead of moving along the x-axis, like dx, or the y-axis, dy, like going left to right or up and down, then instead we're moving along the curve C. Now the curve may be on the x, the y, the z, wherever, but we're moving along the curve. Okay? So sometimes people think of this ds right here as the line integral of f with respect to okay, so like if it was dx, it'd be the integral with respect to x. If it was dy, it'd be the integral with respect to y. We change our thinking here a little bit. It's the line integral of f with respect to the arc length. Remember, lowercase s, even in trig, was arc length of a circle. You know, we've had some equations in here where we've had a lowercase s and it was related to arc length. So it's kind of like, you know, if you think about arc length, kind of like the differential of the arc length in a way. ds is equal to the square root of dx dt squared plus dy dt squared. dt. So, I mean, it's not a coincidence that ds is used for arc length and for line integrals. It's the same notation. The way that your book explains this, and you don't have to write this down, I'm gonna read some stuff out of the book now. It says to introduce the concept of a line integral, consider a mass of a wire of finite length given by a curve C in space. So think about the mass of a wire that has a measurable length given by a curve in space. The density of the wire at a point would be f of that point. If we partition the curve into n subarcs, so let me show you a picture of what we're talking about. We can only visualize so much. So let's say that we took this wire and we partitioned it, this curve, into n subarcs, meaning n pieces there. Then the length of the ith subarc is given by delta S sub I. That would be the length of the nth subarc. So whatever arc you're looking at, you're looking, at some piece, then the length of the ith subarc would be given by delta S sub I. All right, so if we choose a point in each subarc, and the length of the subarc is small enough, then the mass of the wire could be written as approximately the sum I equals 1 to n of f of x sub I, y sub I, z sub I, delta S sub I. So that's how your book explains a line integral, by imagining the mass of a wire with finite length. So the official, definition here could be written with this summation, because any integral can be written with the summation notation. Because remember even when we were doing the two-dimensional integrals, we were summing up an infinite number of rectangles. Now it's like, instead of doing that, we're subbing up an infinite number of arcs. If the partition is small enough, or the subarc is small enough, and we sum up an infinite number of those subarcs, then we would have the length. Okay, I don't know if that helps any, but we do need to remember the ds, like right here. This ds right here is going to be the square root of dx dt squared plus dy dt squared dt. Of course, that would just be in 2 dimensions. In 3 dimensions, then we would just have to add that third part the z of t, dz dt. All right, so let's do a line integral. I've talked about it enough. A lot of the stuff probably didn't make a lot of sense, but the more that we work them, maybe the better we'll understand. All right, so we are going to find the line integral of I'm going to give you a figure. Now, if I didn't give you the curve, then we would have to figure out the curve, you know, the parametricization. We'd have to figure out the parametricization. All right, but the actual problem that we're doing, we're going to find the line integral over x squared minus y plus 3z ds. Now, x squared minus y plus 3z is not the equation of that figure. Okay. Now what we want to do is, the way we do this, we start by writing the parametric form of the equation of the line segment, just like we did before. We only have one piece here, though. All right. So we need to figure out the parametricization of this smooth curve C. So for this smooth curve C, x of t will be equal to, all right, let's see, we're going from 0 to 1. So let's, for all three of these, I'm going to need a little more room. For all three of these, let's let t be greater than or equal to 0, less than or equal to 1. When we can do that, that's probably the best numbers to use, because we're used to 0 and 1. All right, so x of t be equal to, so when I plug in a 0, I want to get out a 0. When I plug in a 1, I want to get out a 1. So it'd just be t. That's right. And then y of t is equal to, when I plug in a 0, I want to get out a 0. When I plug in a 2, when I plug in a 1, I want to get out a 2. So it should be very similar to that. Just what? 2t. And lastly, I want to go from 0 to 1. Well, we know that. We just figured it out for x, right? When I plug in a 0, I want to get out a 0. When I plug in a 1, I want to get out a 1. So z of t, just be t. All right. So that's our parametricization. So now we're going to have to solve, or we're going to have to write in what ds is equal to. And ds is, remember, ds is the square root of each derivative squared. So I wrote it as dx dt last time, but how about x of t prime squared plus y of t prime squared plus z of t prime squared. You can write dx dt x prime of t, same thing. So what's our derivatives? So we got x prime of t is 1. Y prime of t is 2. Z prime of t is 1. All right. So this ds is going to be equal to, remember we have dt at the end now. ds is going to be equal to 1 squared, the square root of 1 squared plus 2 squared plus 1 squared, which is square root of 6 dt. Now since we have dt, we have to change our function that we're integrating over in terms of t. We're not going to have x, y, and z anymore. We're just going to have what they are equal to in terms of t. Well, x is equal to t. So when I rewrite my integral now, this is going to be the integral of, if x is equal to t, then what will x squared be equal to? T squared. Right? Minus y is equal to 2t. So 2t. Plus, and then z is equal to t. Plus 3t. So all be dt. And this part right here, the ds was a constant. The ds is square root of 6 dt. So I can write that in front like that. You can write it behind if you want to, but it means the same thing. So if you're more comfortable, let me show you. If you're more comfortable writing this, that's okay. It means the same thing as this. Now, I do have two like terms here that I want to put together because I don't want to integrate 3 terms if I can just integrate 2 terms. So what's negative 2t plus 3t? Just plus t. What do you think our boundaries are for t? That's what we made it. We made it 0 to 1. If you make it 0 to 1, then you have to use those boundaries. If you make it 1 to 2, and you come up with different equations that work out, you have to make it 1 to 2. We'll get the same answer either way. Well, we use 0 to 1, so that's the boundaries on my definite integral. All right, so this is equal to the square root of 6 times, now let's integrate, t cubed over 3 plus t squared over 2. And we're going to evaluate that from 0 to 1. So it's the square root of 6 times. Plug in a 1. 1/3 plus 1/2. Plug in a 0. 0, 0. Alright, so 1/2 and 1/3, those are both 6. So 2/6 and 3/6. It's going to be 5/6. So 5/6. What happens when I multiply the square root? How about 5 square roots of 6 over 6? All right. While it would make the integral harder, what I've told you twice here, I'm about to tell you again. It would make the integral harder here, but look what your book says here. The value of the line integral in example 2 does not depend on the parametrization of the line segment C. Any smooth parametrization will produce the same value, or same answer. To convince yourself of this, try some other parametrizations. So, to find a different parametrization, you would have to let t be different values. So as long as, like if you let t be greater than or equal to -1/2, less than or equal to 0, then these are the 3 equations that you would come up with. That your x, your y, and your z. Yes. it would make it more complicated. But if you do all the same work, you get the same answer at the end. Same with this. If you let, I probably would never use fractions unless I had to. If I had to let it be something different, I'd probably use 1 to 2 or something like that. But if you go negative 1 to 0, these three equations work out for negative 1 to 0. That probably wouldn't be too bad. It's just when I did my definite integral, I'd have to say negative 1 to 0. I'd have to take these three derivatives and plug them into my ds formula. But again, get the exact same answer. So that's why I prefer to use 0 to t when I can, because 0 to t is really easy to work out. I said 0 to t, I meant 0 to 1. I'm sorry. Alright, I probably won't have time to finish this one, but I want to get started on it. So we are going to evaluate the integral, the line integral. Anytime you see the c down here, that's a line integral of x ds over this smooth curve. All right, so you can see the equations are changing here in this smooth curve. It's telling you it's just telling you what the curves are. So, all right, so for c sub 1, and the reason why it tells us what the curves are is because any values we plug in, we need it to also match the curve if we have a different equation. If that makes sense. If it doesn't, don't worry. I'm going to show you. So c sub 1, how could I write that? This would be, I'm going from 0, 0 to 1, 1 for y equals x. So I could let x of t, or if you want to use shorthand, you can just say x. But I'm just going from 0 to, wait, I'm letting t be what? Greater than or equal to 0, less than or equal to 1. So I could just let x equal t, that'll work out. Then what would I let y equal if I want to go from 0 to 1? Same thing. All right, for the second part, I'm going from 1, 1 to 0, 0. Now, whatever I have to write in, whatever I write in here, though, I have to keep in mind that it's along this parabola. So, if I let x equal, how could I wouldn't want to go from 1 to 0. I'm not plugging in a 1 and a 2 is what the point that I'm trying to make. I still want to go between 0 and 1. So to get x here, if I plug in a 0 and get out a 1, and plug in a 1 and get out a 0, I'm going to have to let it be 1 minus t. Plugging in a 0 gets out a 1. Plugging in a 1 gets out a 0. Now here's where I can use my equation here to get what y has to be equal to. Because if x has to be equal to this, y has to be equal to 1 minus t squared. Because this is x squared. Okay? See if you can set up these two integrals, as we have two parts. Okay? And that's what we'll pick up next time.